Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and uncut. So we have another medium today. Looks like we have another graph problem as well. So what we have is we have some int. It might be so that's the number of nodes, which are zero indexed, and you're also given all the edges. So you're given the edges array. Most likely we'll have to turn that into adjacent list, but let's see. So, uh, so also the edge is undirected. So return the number of complete connected components. So a connected component is a subgraph in which there exists a path between any two vertices, and no vertex of the subgraph shares an edge with a vertex outside. Right. So this is just finding connected components, right? Yeah, I think we have a very easy problem today then. Yeah, this is just finding well, like connected components. Wait, right? Hi, wait. That's not true actually. That's not true because if we look at this, so we have a triangle and then we have this, but apparently the output is 1 here. So component containing vertices 0, 1, and 2 is complete. Since there's an edge between every pair. Right, so it has to be, so every node has to connect to every node. Yeah, but also the bounds are actually extremely small, so we can actually brute force this. Yeah, okay, so the component containing vertices 3, 4, and 5 is not complete since there is no edge between 4 and 5. Right, so connected means yes, there exists a path between any two vertices. And actually this is oh wait. I missed the definition here. Is said to be complete if there exists an edge between every pair of its vertices. Right. So so what we can do is we can just find connected components normally, and then after we find like the connected components, we just check whether there's an edge between each of the node in that connected component. And if it does, we can just return we can just return, like we can just add 1 to the number of completed connected components. So complete components. So set it as 0, and of course we do need the adjacent list. So that's very super common in these questions, especially when they give you an edges array, because it's very hard to like loop through them. Like it will take too long basically. So what we want to do is we want to do this. So for range n, so we will have we'll have a list for each of the node, and then now for the two ends in the edges, we'll do adjacent list a, and because it is undirected, we need to do it for both sides. And then what we want to do is we want to find the connected component, right? So we actually also need a scene array. So scene false for something in range n. Yeah, actually, do I just say underscore here? But basically this means like you're not going to use that variable. Like instead of using I, it's just better code. Yeah. So now for I in range n, so we want to loop through each of them. If I is not seen yet, so it is not in any components yet, we want to run some like find connected components or something like that. Find connected. Oh wait, actually we can just do so number of complete components. So we want to add 1 if is complete component. So we write that function maybe like here. So def is complete component, and then we have the starting node, and then like we can do the we can find the connected component down here, and then yeah. But basically, we'll do this in this function here. So, but if if it is a complete component, like for whatever connected component I is in, and otherwise we just don't add anything there. And at the end, we just return the number of complete components. So now what we have left is, well, completing this function. So I think what we want is we want a set which stores like which component which nodes are in this components, and then we need a function called probably like DFS. So we can just we can just traverse out and just find all the nodes that are connected, like they are in the same connected component with this node. Yeah, so we can just do let's think. Yeah, we can just do like maybe like I or something. So that would be like which node it is. Maybe we'll call this the roots. It doesn't really matter, but we'll just call it that. Don't actually have to return anything. We just have to do DFS. So so we're gonna do nodes.add node, and so for next in adjacent list node, so that gets all the neighbors. So if next is not seen, we want to DFS on it. So seen. Oh wait, yeah, next, and then here we want to add next to seen, because we have seen it now, so we can turn it into true. So here we just have to run the function on the root to get all the to get all the nodes in the current connected components. So that's why we have this. Hey, actually we can use a list. It'll be a parent y very soon. Yeah. So now what we can do is we can do for we can do for I in range length of nodes, and then for j in range I plus 1 all the way to length of nodes. So that's going to give us all the pairs. We can just do if adjacent list. Oh wait, what if we, I think we need another data structure here to make it fast. So we can just store edges as sets. So we make a set here, and then we just do edges set. We want to add AB, and then we want to add BA, and here we get every node, like we get every pair of node like in this connected component, and we have to check whether there's an edge between each of them, right? So what we can do is we can just do call it edges set. Yeah, so if edges set contains, well, ij, well, actually it should be nodes I, nodes j. If it does contain that, then, well, actually nothing happens because it works. But if not, we want to return false. But if all of them works, like all of them has an edge, then we want to return true at the end. Yeah, I think this should work. Cannot access local variable next, where it is not associated with a value. Oops. Would have been a tragic mistake that will probably take ages to find. Yeah. So we got it. Yeah, when I'm coding, I do realize there's a better way to do this. So you can see that this is an n square, like this has an n square time complexity, right? But like one thing to notice is that for any graph, like for any connected component, if you if you do a BFS, so let's say BFS out like this, if you do a BFS, and it has like any depth to nodes, well, that means these are not connected. So that means like you can return earlier. So that's like some optimization that you can do. But it is true that like if you do like one BFS and there are like nothing outside, well, you still have to check like whether these are all connected or not. But yeah. I guess like another thing you can check. Yeah, honestly, I think this is still n squared. So yeah, the time complexity of this is going to be n cubed. But yeah, is it n cubed? No, it should be n squared. Yeah, it should be n squared. Cause like, is that true though? No, I think it's n cubed. I'm confusing myself. Wait, so this is ON, but then we like, so if we have like n connected components, then this is going to be like O1, right? Because there are only one element. But yeah, I think this is n squared. But yeah, if I'm wrong, well, comment down in the comments, and write an argument for that. But yeah, yes, it's not the hardest question today. We have gotten into the graphs question though, which is not too ideal for me. I'm very weak on graphs. But yeah, thanks for watching, and I'll see you tomorrow. Bye.